In this presentation, we are going to look at osmosis in living tissues, evaluating the effects of various solutions on strips cut out of a petiole or stalk of a cocoyam. My name is Lenya Jude Fanba. I am a holder of a Bachelor of Education degree in Life and Earth Sciences from the University of Marua, Cameroon, and a Doctor of Philosophy degree in Clinical Biochemistry from the University of Chang, Cameroon. This experiment is based on osmosis in living tissue. As a reminder, osmosis is the movement of water across the cell membrane from a solution of high water potential to a solution of low water potential. The experiment is also based on the fact that the cocoyam petiole has an outermost cuticle, which is non-cellular and rigid, and thus does not respond to osmosis. This cuticle covers inner hypodermal and cortical cells, which are living and flexible and can respond to osmosis. To better understand this experiment, let us look at the transverse section of a monocot stem. We see at the surface there is a non-cellular cuticle covering the stem. Below the cuticle is the epidermis, made up of a layer of cells. Then follows the hypodermis, in which are scattered sewer chlorenchyma cells, thus giving the stem a green appearance. Deep within the stem is the cortex, or the ground tissue, in which are found scattered vascular bundles. The varied response of these parts to various solutions will give us different results in this experiment. As hypothesis, we can say, osmosis occurs only in living tissues and not in dead tissues or non-living matter. We are going to use a set of materials and solutions, including a cocoyam petiole or stalk, which is the biological material, the living tissue. As a tip, the petiole of local variety, Macabo cocoyam, gives clearer results. We need a scalpel to cut out strips from the petiole. A razor blade can also be used. A millimeter graduated ruler is needed to measure the dimensions of the strips. An electronic balance will be used to measure the masses of strips. A tissue paper will be used to blot off solutions from the strips. We also need 4 beakers to hold the various solutions, 4 petri dishes as recipients for the strips and solutions during the experiment, and a wall clock with a sweeping second hand for timing. We are going to use 4 different solutions. Distilled water will serve as the hypotonic solution. A 0.5 molar sodium chloride solution made by dissolving half the molar mass, 29.22 grams, of the salt in 1 liter of distilled water will serve as a less hypotonic solution. A 1 molar sodium chloride solution made by dissolving 58.44 grams of the salt in 1 liter of distilled water will serve as a highly hypertonic solution. A 1 molar sodium hydroxide solution made by dissolving 40 grams of pellets in 1 liter of distilled water will serve as a corrosive solution, which will kill the tissue and provide the control along the noncellular cuticle. From the cocoyam stalk, we will cut out 4 strips following the following directives. Using a scalpel, make a clean cut at one edge of the petiole. Use the ruler to measure out 5 centimeters section of the petiole and cut with a scalpel. Now cut out from this cylindrical section of the petiole 4 strips each with 0.5 centimeters width of the epidermis and equal quantity of the cortex. Notice that as you start cutting out the strips, the flexible cells of the cortex are released from the constraint of the cuticle and expand, causing the strips to curve outward over the epidermis. Note the degree of the curvatures then. Use a balance to measure the masses of the and record these before immersion into the solutions. Using a label tag, label 4 petri dishes on the side as distilled water, 0.5 molar sodium chloride, 1 molar sodium chloride, and 1 molar sodium hydroxide. Place each strip in a petri dish and pour the respective solutions to completely cover them. Allow the setup for 30 minutes using a wall clock for timing. As a reminder, in the report, you are expected to use reported speech. That is the simple past tense for the procedure, observations, and results as concise as possible. For this procedure, a sample report can be: a 5 centimeter long section of the cocoyam petiole was cut using a scalpel ruler. Using a scalpel, 4 strips were cut out of the section with 0.5 centimeter width of the epidermis and the cortex. The curvatures of the strips were noted and the masses were measured using a balance. 4 dishes were labeled: distilled water, 0.5 molar sodium chloride, 1 molar chloride, and 1 molar sodium hydroxide. The strips were placed in each of the dishes. The respective solutions were poured over the strips to cover them. The setup was allowed for 30 minutes. After the 30 minutes, the strips were removed and blotted using tissue paper. The curvatures and mass were again measured. The results of the experiment are presented as shown on the table. We saw an increase in curvature of the strip put in distilled water. That is, the hypotonic solution. The mass of the strip also increased. There is a reduction in the curvatures of the strips in the hypotonic solutions. For a lesser concentrated 0.5 molar chloride, the curved strip redressed to nearly straight. While in the more concentrated 1 molar solution, the curvature overturned and the epidermis curved over the cortex. There was also a reduction in the masses of the strips. There was no noticeable change in the curvature of the strip in the 1 molar sodium hydroxide solution. The strip appeared cooked and had a slight reduction in mass. Let us now give meaning to our results. For the strip in distilled water, we can say, distilled water is hypotonic to the cells in the strip of the cocoyam petiole. That is, distilled water has a higher water potential than the cells. Water moved into the cells by osmosis. The tissue gained water, which accounts for the increase in mass. The cells became distended due to influx of water. This distension of cells led to the overall increase in length of the strip, while the non-cellular and rigid cuticle was not affected by osmosis. Hence, the extending cortex curved over the epidermis, and this increased the curvature of the strip. We can say for the strips in the sodium chloride solutions that, at these concentrations, the sodium chloride solutions are hypotonic to the potato tuber, whose concentration typically ranges from 0.1 to 0.3 molar. So the solutions have a low water potential than the cells in the strip. Water moved out of this by osmosis into the solutions. The tissues lost water, leading to decrease in mass observed. The cells became plasmolized and shrank, leading to an overall reduction in lengths of the strips. The retraction of cells bound to the rigid cuticle caused the strip to curve inward under the cuticle. Less water in the 0.5 molar sodium chloride solution, which is weaker than the 1 molar sodium chloride solution, leading to the differences in reduction of curvatures and masses of the tissues. For the 1 molar sodium hydroxide solution, the solution is corrosive. It thus killed the cells, making the strip to have a cooked appearance. The cells lost their selective permeability due to denaturation of the cell membrane and its transporters. No osmosis occurred, and there was no appreciable change of mass and curvature. This setup served as the control as the cells were killed, and no evidence of osmosis was observed. That is, no change in curvature or mass of the strip. From these results, we can conclude with affirmation of our hypothesis that osmosis occurs only in living tissues and not in dead tissues or non-living material like the cuticle. To arrive at these results, we took some precautions that helped us to have reliable results, and also for safety. The dishes were appropriately labeled with names of the solution to avoid confusion of the solutions. Strips were completely covered so that the solutions affected the whole strip. The strips were removed from the solutions using forceps and blotted with tissue paper to avoid burns by the corrosive solution. Blotting was done gently to avoid squeezing the softened strips, which could affect the masses. We may need to plot the graphs of changes in mass and curvature against the various solutions. Using the data from the results, we will have the following line graph for the mass. We use the absolute values of the changes. To plot for the curvature, since we did not use numerical measures, we choose a hypothetical number, say 3, to be the curvature before immersion, and any increase in curvature is assumed to be a value above 3, and a decrease takes a value below 3. For example, we see an increase from 3 to 5 in distilled water, and a reduction from 3 to 1 in the 1 molar sodium chloride solution. Let us also identify the variables in this. The independent variable is the concentration of each of the solutions. They are set at the beginning and do not vary during the experiment. The dependent variables are the changes in length and mass. The constants are the living tissue. We use strips from 1 cocoyam petiole, the time, The strips were placed in the solution for the same duration, the temperature, etc. We have come to the end of this presentation. Our next presentation will be on the effects of osmosis on a peeling of the lower epidermis of Tradescantia. Thanks for your time. Hope you enjoyed following up the presentation. Please subscribe to this channel, like, and share. By subscribing, you will be getting notifications when new presentations are available.